All right, looks like the recording has started. Thank you everyone for coming to this presentation by Professor Trnka. It's sort of this collaboration between the Physics Club and quantum computing at Davis. And we're very excited to have him here and honored as well. And we definitely look forward to what there is to come. So without further ado, I will let you go ahead and kick things off and get yourself situated, Professor. But once again, thank you so much for your time.
Okay, well, thanks a lot for the invitation. Yeah, I'm happy to talk to you about some research in theoretical physics. So it will be kind of an overview, impressionistic talk. There will be not many equations and so on, more based on some principles. Of course, feel free to stop me and ask any questions. I will not go into the details for most of the things. So yeah, just to give you some basic idea what is going on in this field. So the topic of the talk is to give you some insight into new methods in quantum field theory related to particle scattering. And it kind of touches the most important and the most difficult questions in theoretical physics, and that is understanding the fundamental laws of nature. So what are these laws, especially how they are connected to the interactions of elementary particles, where these laws are revealed. What is the connection to cosmology, about the questions about the universe, why it's big, and what is the theory of everything? So is there any theory which can kind of describe the whole universe at both microscopic and microscopic level? And one way how to probe these fundamental laws is to study the interactions of elementary particles. So all of you know, like, what are the basic physical forces, interactions, like electromagnetism, gravity. There are also weak and strong nuclear interactions, and they manifest themselves at a microscopic level in the way how the elementary particles interact. And we have a menu of all particles, which is called standard model. And we know how they interact with each other. And they can interact through electromagnetic force, through these strong and weak nuclear forces. Gravity is more special. Everybody interacts gravitationally. Now, the latest addition to the standard model was the discovery of Higgs boson a couple of years ago. But we know that the standard model is kind of an effective description. It's not a complete description of nature. It works very well if we look at some energy range, but it's there is more physics beyond that. And people are actively looking, experimentalists are actively looking for discovering this physics at various particle experiments, such as colliders, neutrino experiments. And there are many theoretical proposals what this physics can be. And yeah, it's a very active area of research. Now, from the theorist perspective, we would like to be able to describe what is going on in these interactions and predict what happens. And theoretical framework to describe the quantum physical systems which is compatible with both principles of special relativity and quantum mechanics. So takes into account the speed of light and all the consequences of special relativity, but at the same time also is based on the quantum description of the world, not the classical description. And this framework is called quantum field theory. Quantum field theory was developed first kind of formulated by Dirac in 1930s, and then later developed by Feynman, Dyson, Schwinger, and others in 40s and 50s. And in this framework, the elementary particles are described by mathematical objects called fields, and their interactions, which are these physical forces, are described by Lagrangian. The example of the quantum field theory for electromagnetism is called quantum electrodynamics, and the elementary particles are here electrons and positron, and the photon, which carries the electromagnetic force. And the Lagrangian has this schematic form. It involves the strength of the interaction, which is also called coupling constant, and the presence of these fields tells you what is the elementary interaction. So in this case, the elementary interaction is when two electrons interact with photon, or more precisely, it's electron and positron which interacts with the photon. And we associate a picture with this interaction. So just reading off from the Lagrangian, we can draw this picture. Two electrons meet at a point and emit a photon. Now, this framework can be used to predict the outcomes of particle experiments. So the quantum mechanical approach to physical systems says that the results of all experiments are probabilistic, not deterministic. So once we have some initial state, in this case, in the scattering process, we take two electrons and we smash them together. We don't know what happens in the end. Yeah, there are just many options, and actually infinite number of final states can occur. And everything is probabilistic. So each of these final states has some probability to happen. And these probabilities are calculated by mathematical objects called scattering amplitudes, which depend on the initial state and the final state. And for example, the simplest thing that can happen is that two electrons interact and produce, and again, two electrons. This amplitude, even in this case, is not trivial. It's a function of energies and angles of these particles. But we can have more complicated case when actually in the final state, we have additional photon, or we can have free photons, or any number of photons. And for each of this process, we can associate this function called scattering amplitudes. The probability is then related to the squares of scattering amplitudes. And the sum of all probabilities for all final states to happen must be equal to 100%. So this is called unitarity in this context. Now, the big question theoretically is what happens inside this blob. Yeah, so obviously something happens when the electrons interact and produce these final states, and how to describe it theoretically. And that's what the quantum field theory gives you. It gives you kind of a guideline of how to think about it. So let's say in this simplest case, when two electrons interact and produce another two electrons, we have this mathematical function called scattering amplitudes, which is related to some probability. Now, we need to we have to consider that the interaction, this coupling constant Q is small, so it's a weak coupling. Yeah, they don't interact strongly. Then the system is qualitatively different. But if they interact weakly, then the force is weak. Then we can expand in like a Taylor expansion in Q. And the dominant piece will be 1 in this case. And we then associate a picture called Feynman diagram with that process. And you can see it on the left. It just means that the electrons don't talk to each other at all. Now there is a subleading piece, which is now proportional to Q square, which tells you that some interaction happens. You associate different Feynman diagram, and you can see it in the second picture. The electrons exchange a photon. Now there are two vertices in this graph. Each vertex brings 1 power of Q, so that diagram is proportional to Q squared. And then you can consider higher and higher orders, and you just draw more and more complicated Feynman diagrams. The general rule is that you should draw all Feynman diagrams, which represent all possible processes that can happen. And it is organized in this power of Q, which is called also perturbation theory. and more and more complicated diagrams have higher powers of Q and are suppressed if Q is small. Okay, so this is a diagrammatic picture how to organize the perturbation theory. And in fact, it is an expansion of a path integral of the following form. Now, if you look at these diagrams, they correspond to these different powers of Qs, but they are also diagrammatically, the difference between them is the number of loops they contain. You can see that the second diagram we call tree level because it doesn't have any loop. And once you add more loops, you get loop diagrams. So for example, this term proportional to Q to the 4 has diagrams which have 1 loop in it. If I draw this Q to the 6, they would have 2 loops in it and so on. So this is also called loop expansion. And yeah, the simple diagrammatic is to draw all Feynman diagrams, and you always calculate at a given order in Q, so you just draw all Feynman diagrams which have given number of loops in it. And each diagram contributes to the amplitude. There are certain rules called Feynman rules, how to turn the diagram into a formula. Yeah, so there is this diagrammatic part, and then there is the analytic part, and you have to convert these diagrams into the formula. And this is and this is content of many textbooks and even courses here at UC Davis. Okay, now using this theoretical framework of quantum field theory, one can start to introduce theories which describe the interactions of elementary particles. Now this went gradually. People introduced this quantum electrodynamics, describing electromagnetic interactions. Then they added also weak interactions. The final theory is called electroweak theory or electroweak interactions. It contains some important things like Higgs mechanism, which explains why the particles have mass and so on. But in the end, you just write a Lagrangian, which describes your fields and interactions, and they are just correspond to these elementary pictures, these Feynman vertices, which tells you how particles interact. Yeah, so you can see here some interaction of H corresponds to Higgs boson, W to W particles. So these pictures tells you how elementary particles interact, and then they can be converted into formulas. Now, when there is one special interaction called strong interaction, corresponds to or is responsible to nuclei of atoms to hold together. And it has some very interesting feature. At very high energies, if the particles have huge energies, you can see two types of particles, quarks and gluons. Quarks are the elementary particles, and the gluons are the ones which are responsible for carrying this interaction. However, at low energies, the particles are slow. These quarks and gluons cannot be observed. They are trapped inside particles like protons and neutrons. Okay, and this is called confinement. So you have these elementary particles, quarks and gluons, but at low energies, they are trapped. They are not free, they just have to stay inside these other particles called hadrons, and protons and neutrons are most important representatives for that. So there is a big kind of question how to, this theory is called quantum chromodynamics, and there is a big question to see this behavior, how if you have these quarks and gluons, how do you explain that on one side, if they are very fast at high energies, they are free, and at low energies, they are confined. Okay, now the quantum field theory as a theoretical framework has been extremely successful. As I said, it was formulated in, let's say, 1940s. And in the last 70, 80 years, it has passed countless number of different checks. And kind of the most, the best known check is the calculation and comparing with experiment of the quantity called magnetic dipole moment of electron. It's certain magnetic property of the electron, which was first theoretically calculated or predicted by Dirac in 1928. There is some dimensionless quantity, which he labeled G or GE for the electron. And he calculated that it should be equal to 2. And this was also confirmed by experiment at the same time. In the modern Feynman diagram language, which he didn't have at that time, it would correspond to calculate the Feynman diagram, which is here on the left. And then there was a correction to it, calculated by Schwinger in 1947, when this correction was small, so it just added some decimal digits to this value, and it was again confirmed by experiment to the same precision. And then it continued, and if you calculate these more and more complicated Feynman diagrams, higher and higher order amplitudes, you get bigger and bigger precision. You can compare it to experiment. And when we get to the 2-loop amplitudes, this is a representative Feynman diagram, which has 2 loops inside. You already get such a precision that the theories had to wait 15 years for the experimentalists to get to the same level of precision to confirm that the quantum field theory gives the right prediction. And and then it continued with more and more loops and higher and higher precision. And this quantity is one of the best theoretically predicted quantity in the world. I think it goes like to 17 or something like the decimal digits. Yeah, and it agrees with the experiment up to this precision, which is pretty remarkable. Okay, now as I said, the standard model is not a final theory for describing the elementary particles and the fundamental forces. And we have to go beyond the standard model. Yeah, there is evidence that there is more physics. And the way how theorists handle that is that they have to come up with a new theory. Yeah, what predict new particles, how they interact with the standard model particles, and so on. And the way how to do it is to write down the Lagrangian, which contains these new particles and interactions. And this will necessarily lead to some new predictions of certain processes. And this is something that can be then measured experimentally. Okay. And there are many different proposals for what this beyond standard model physics can be. Kind of the most, the leading proposal for that is supersymmetry, which tells you that in addition to our particles, we can see in the world, the standard model particles, there is a kind of a twin particles called supersymmetric particles. And they are much heavier, so we cannot see them at the moment at these colliders, but they exist and they have exactly the same properties. And that explains a lot of kind of challenges that we have with the standard model. Now, there is also a big question about do all these forces that we see in the world actually, are they unified into a single force? Yeah. Is there a description when all the forces are unified in one? And there is a lot of evidence that this unification can exist. If you go to very high energies, there is only a single force. But if you then go to low energies, you can see kind of different phases of this force. And therefore, we have this electromagnetism and these strong and weak interactions, despite they really come from a single force. Okay, now from just the theoretical or mathematical point of view, QFT is a very interesting, the quantum field theory is a very interesting framework to think about new mathematical ideas, and many mathematicians made huge contributions to this field. There is also a lot of evidence that this way, how I introduce the quantum field theory using these Feynman diagrams and Lagrangians is actually not complete. It's not completely sufficient to describe the physical work. And there was one caveat, if you remember, I said that the coupling constant, the strength of the forces had to be small. And if it is not small, naively, we cannot do any calculation. Yeah, kind of the physical system is too complicated, it's strongly coupled, and the standard formulation cannot be used. However, now we have a lot of evidence that we can actually do these calculations using different tricks. And one of the most important kind of concept here is dualities, which tells you that if you do some calculation at weak coupling, where G, some coupling constant G is small, it actually also describes a different physical system when you replace G by 1 over G. So in that case, 1 over G is huge. Yeah, so the coupling constant is big. So there is some dualities between weakly and strongly coupled systems. And now there is, so this is what is not explained in this standard framework using Feynman diagrams, but there is actually even kind of more conceptual problems and with this formulation, and it is the tension between quantum field theory and gravity. Because the way how I introduced this formalism cannot be really applied to gravity. It has some problems with even defining what are elementary particles in the presence of gravity, or how to think about them. Now there is a way how to unify the quantum field theory and gravity together to give the quantum description for gravity, and this is called string theory, which avoids many of the problems in this unification of quantum field theory and gravity by talking not about elementary particles, about just point objects, but one-dimensional objects called strings. And then instead of Feynman diagrams like here on the left, when you have when kind of the particles meet in one point, giving rise to these Feynman diagrams, we have strings which interact, and the kind of string Feynman diagrams are thick, as you can see here in this picture. Okay, sorry, I don't have access to chat because I'm in this presentation mode. So if you have any question, just unmute yourself. Okay, and we also offer courses on string theory here at Davis. Okay, now there is another aspect of this attempt to describe gravity in the context of quantum theory, and that is related to the other thing I said about dualities, and where the quantum field theory can be dual to string theory, in a sense that if you are at weak coupling, you get string theory, or if you want some theory with gravity in it, and it is dual to another theory at strong coupling, which doesn't have any gravity in it. There is no gravity, but that theory is strongly coupled. Okay, this is called ADS-CFT correspondence, and solving this strongly coupled quantum field theory, which is very hard, you get some information about theory of quantum gravity on the other side of the duality. So this is kind of a direct way how to try to understand what is this quantum theory of gravity. Anyway, there are also some questions about how the quantum field theory can be applied to the whole universe. So far, I was talking about elementary particles, but we want to describe everything in this framework. We also have to understand how the universe expands and what is the role of dark matter, dark energy, which are still kind of things which are not understood, especially with dark energy, about cosmological constant and so on. Anyway, so here kind of the punchline is, if there is a completely new formulation of the quantum field theory, we should see some footprint, or we can, if there is, we might see some footprint of that in the weak coupling regime. So this is where these Feynman diagrams should work perfectly. That's how it was formulated by Dirac and Feynman back then. And the objects that we typically calculate here are scattering amplitudes in these scattering experiments. So if you look at them more closely and we see something new, something interesting, it might very well be the hint that there is a completely new formulation for quantum field theory. Now, the theory, or the interaction which is interesting in this context, is the strong interactions I already discussed, these gluons and quarks. And the reason for that is, if you do the scattering of particles at these colliders, then the dominant interaction is indeed this strong interaction. So if you actually do the calculations and would like to predict what happens, the dominant force is the strong force. So in order to make accurate predictions, you have to calculate amplitudes in this quantum chromodynamics. And the standard procedure, as I said, is to draw Feynman diagrams and evaluate them. And this is just notoriously very complicated. Yeah. So there is a very nice story how people saw some very unexpected behavior, or very unexpected features of these scattering amplitudes going back to 1980s, when the status of the art, if you just use this textbook formulation, and the status of the art of doing these calculations of scattering amplitudes using Feynman diagrams, was calculate the process when you have two gluons which scatter and produce three gluons in the final state. And if you do brute force calculation, draw the Feynman diagrams, there is 24 of them, evaluate them, you get roughly 20 or 30 pages of algebra, like what I see here, when each of these small terms are just some scalar products of different kinematical variables, momenta, polarization vectors. So maybe this is just the answer, and not every question in physics is guaranteed to have some simple answer, but people actually needed to do these calculations, and there were new colliders in progress, and there was a demand to get new and new calculations done here. And the next one on the list was the scattering of two gluons and within the initial state, and four gluons in the final state. And this calculation was done in 1985 by Park and Taylor. And this required to draw 220 Feynman diagrams and evaluate them using these rules. And the result was roughly 100 pages of algebra. That was the final result. And we just did it by hand. Yeah, there were using certain supercomputers back in 1980s. Now they wrote a paper on this result, and they used some compressed notation, and they wrote the result on 14 pages. And this is how it looked like. And they even made some comments that they are hoping to simplify these 14 pages into something simpler to get some better insight on the result. However, or moreover, they actually managed to simplify it into a single line formula. So this is the result for the scattering amplitudes, or more precisely for the square of the scattering amplitudes, which is related to these probabilities. And all these 100 pages, which they wrote as 14 pages of some complicated algebra, can be simplified into a single line. So the final result is much simpler than these individual Feynman diagrams. And this simplicity is completely invisible in these Feynman diagrams. So that kind of changed the strategy of how people handle these calculations. And there was a big question: if the scattering amplitude results are so simple, what is the scattering amplitude? Is there some question to which the scattering amplitude is the answer? Obviously, we can use the standard method of Feynman diagrams, and of course, it is used in many different contexts because it's still good, despite it produces these kind of overly redundant answers. But maybe there is a different way how to think about it. And yeah, and one way how people wanted to answer that question is to say that the scattering amplitude is certain mathematical objects which is fixed by certain properties. But this was the idea even going back to 1960s, when they failed to actually use it as an efficient method to do any calculation. But in last 10, 20 years, people were able to kind of unify both these methods, both the Feynman diagrams and on one side, and this picture of uniqueness of some mathematical objects on the other side, to actually make huge progress. And yeah, and there have been many new methods to do these, calculate these amplitudes beyond just Feynman diagrams, which are much more efficient. However, I would like to talk about something else, not about directly efficiency, but about a completely different picture for what this particle scattering is. And it all started in 2009, when Andrew Hodges, who's a physicist or mathematical physicist in Oxford, studied one of this particular new method to calculate amplitudes called recursion relations, and he use it and studied the individual terms in this new expansion, not the Feynman diagram expansion. And the motivation was to use something called Twistor variables, which were introduced by Roger Penrose in 1970s in his own attempts to formulate quantum gravity using twistors. Yeah. In this new method, instead of these 220 Feynman diagrams that Park and Taylor had to deal with in 80s, there are only two contributions. There are only two terms. And yeah, diagrammatically they look like that. These are not Feynman diagrams, other type of diagrams, but there are only two. And he used these twistor variables and he rewrote them in using these variables in a new form. And the details here are not important, but he just looked at these expressions and they looked familiar to him. Yeah, and he already saw these expressions before, because exactly the same expressions are calculating volumes of tetrahedra in some complex projective space called momentum twistor space. Okay, so with one of these expressions, you can associate one tetrahedron, which has some labels which correspond to the kind of labeling of these elementary particles, or these gluons. And the other expression is associated with the other tetrahedron. And if you combine them together, you get the polyhedron. You kind of chop up one of the corners from the tetrahedron and you get this polyhedron. So these two pieces subtract and they actually triangulate polyhedron. So now, for this case, he get a very different answer for what this scattering amplitude is a volume of polyhedron. Yeah. Yeah, it's a different answer than some sum of Feynman diagrams. Yeah, it's a very direct geometric picture for this scattering amplitude. Now, if this scattering amplitude is a volume of this polyhedron, if that's the invariant definition, then there is also some triangulation, some very obscure one, which breaks this piece into 220 elementary pieces, and each of them is a Feynman diagram. Yeah, indeed that exists. It's obviously not the most efficient way how to triangulate this object. Okay, now this was true for this simplest amplitude that Hodges studied, this amplitude for 6 gluons means that 2 gluons scatter in the initial state and 4 gluons are in final state. But it didn't seem to work beyond this simplest example. There was a problem with all amplitudes at this tree level, and then also these loop amplitudes, the ones which would correspond to this higher order in the coupling constant terms. So there was a need for kind of a bigger mathematical, bigger geometrical space to fit all amplitudes there and realize them as also some geometric objects. And the connection came from mathematics. And around the same time, there were mathematicians who studied something called Playback graphs, okay? For a very different reason, had nothing to do with physics. And also they were studied by two different groups of mathematicians from two different fields. But the connection was that you would like to draw some graph, like you see in the picture, which has only cubic vertices and has two colors, let's say white and blue. And with these graph, you can associate a permutation of, let's say here, 4 labels. So this is one particular permutation, 1, 2, 3, 4 goes to 3, 4, 1, 2. And with the same graph, you can also associate some metrics, 2 by 4 metrics. And it's positive metrics because the minors, 2 by 2 minors of this matrix are positive. Anyway, so there was some mathematical theory, but what happened to be true is that there is a connection with physics. So these graphs, which play this role in mathematics, at the same time also play a role in physics as building blocks for scattering amplitudes. And exactly the building blocks which make these calculations of scattering amplitudes extremely simple. Okay, and then the invariant or the raw information about a given scattering amplitude is given by a set of permutations. For example, in this case, you can just send somebody an email and give him 6 permutations of 7 points, 1, 2, 3, 4, 5, 6, 7. They correspond to 6 these diagrams, which we call then on-shell diagrams. And this is the full amplitude for 7 gluons, 2 gluons in the initial state and 5 gluons in the final state. Note that this is that if you wanted to use Feynman diagrams, you would have to draw and evaluate 2,500 Feynman diagrams. But really, the invariant information is given in just 6 permutations. Yeah, you only need to know that, and then you can turn it into formula. Yeah, there is a straightforward way how to turn it into the actual expressions and get that mathematical object. Okay, but even here, despite this is extremely simple, we went very far. We made all these calculations much simpler. We introduced new objects, not Feynman diagrams, but these new types of building blocks for scattering amplitudes. It's still going back to the question, what is the scattering amplitude as a single object? Yeah, so we are not saying in this case that it is sum of 2,500 Feynman diagrams, but it's still a sum of 6 of these new building blocks, of these on-shell diagrams. Okay, but what is it as one object? And we had already this picture from before in this one particular case when each of these terms could be associated with a tetrahedron. They glued together into some geometry. And indeed, this also happens in completely general case. In some special cases, these amplitudes corresponds to polyhedra, but there is some mathematical generalization which we called amplituhedron, when indeed the volume of the amplituhedron corresponds to these gluon amplitudes. And the amplituhedron is some higher dimensional kind of curvy space. It's not like polyhedron with straight lines and straight faces. Okay. Let me give you some toy example for how it goes. So in some toy example, this amplituhedron is just a polygon in the plane. And these points Z in this picture corresponds to 6 gluons. Yeah, this is just some toy model, so it doesn't really kind of directly describe the physical work, but it works well for this purpose. Yeah, so these Z's, there is an information about the particle, what is the energy, what is the spin, and so on, can be turned into some coordinate Z in this space. Now, if you triangulate this polygon, like here in this picture, you get one representation of the amplitude in terms of these on-shell diagrams. Yeah. So you triangulate it, you get some smaller building blocks, and here it turns out to be exactly these on-shell diagrams. But you can use other triangulation when, instead of using this point Z1 as a way how to divide it into triangles, you choose some arbitrary point Z star in the middle, and then you get a Feynman diagram expansion. Yeah, so the invariant definition of the amplitude is neither of these triangulations, is the fact that the amplitude here, this kind of toy model amplitude, is an area of this polygon. And you can divide it however you want, but once you sum the pieces, it gives the same result. Okay, so, okay, anyway, this is just some full mathematical definition for what the amplituhedron is, but the punchline is that it's a volume of some geometric space. Now, the physics problem then of calculating scattering amplitudes or evaluating these Feynman diagrams turns into a mathematical problem of triangulating some geometric space. And for some case, we don't know how to do it in general. We know what is the definition, but in some cases, you can actually do some calculations to all loops, which means to arbitrary value of coupling. You don't have to rely on the fact that this coupling is small anymore. And this is something which cannot be done using these Feynman diagrams. For that, you would have to sum infinite number of Feynman diagrams. Okay, let me give you the flavor of what this kind of mathematical problem that you have to solve, how does it look like? Yeah, so what do you have to solve to actually get the amplitude from this geometric picture? And yeah, we call it a high school problem because it's easy to explain it to any high school student, but of course it's extremely difficult to actually solve it. So this corresponds to scattering of 2 gluons in the initial state and 2 gluons in the final state, but to any number of loops. So if you want to all orders in this coupling G or Q, I forgot how I denote it. Okay, so what is the mathematical problem? Yeah, what the amplituhedron, if you look what you have to do to triangulate the space, it turns into set of equations which can be interpreted in this way. So we start with the positive quadrant in a plane. And we consider 2 types of vectors, the red vector and the blue vector. And we would like to find all values of these components, x, y, z, and w, which are allowed in the positive quadrant. In this case, it's very simple. The x, y, z, and w must go from 0 to infinity. Both coordinates must be positive. In that case, the vector lies in the positive quadrant. It's very easy. From this information, there is just a straightforward way how to write a volume of this configuration space. Yeah, just writing it here as some differential form. But yeah, that's not the hard step. Once you know what are all these vectors, allowed vectors, then you can just turn it into some volume form, and that calculates the scattering amplitude. Now, suppose that I have 2 pairs of vectors, 2 red and 2 blue. Now, if I don't say anything else, then the configuration space of all these vectors, which are in the positive quadrant, is just that all these variables that are parameterized, these vectors must be positive, and that's it. And then kind of the volume form is also trivial. However, we have to now do something more complicated. We have to say that there is an inequality between these 2 vectors. And the inequality looks like that. It tells you that if you take the difference between these blue vectors B2 and B1 and the difference between A2 and A1, then the scalar product of these differences is smaller than 0, which means that in this picture, this angle must be bigger than 90 degrees. Okay, so we get some quadratic inequality between these parameters. So now not all blue vectors and red vectors will be allowed, only the ones which have this angle bigger than 90 degrees. Yeah, so it's a subset of them. And if you want to find what configurations are allowed, you have to kind of triangulate this configuration space. So this is exactly triangulating the amplituhedron. And if you do it, you can do it, and then you get a certain differential form which calculates the volume of this configuration. Okay, and now this will correspond to this volume form corresponds to a two-loop amplitude now. Yeah, for these 4 gluons. And now for general story, you have L red vectors, L blue vectors, and you have to find a configuration space where any pair of the blue vectors and any pair of the red vectors satisfies this quadratic inequality, yeah, where the scalar product of these differences is always negative. And you have to find all these vectors. You have to find all the configurations of these vectors. If you find it, then you calculated the amplitude of gluons to any number of loops for general L. L here really labels the loop order. Okay, so this is what the amplituhedron basically tells you. This is the type of the mathematical question it poses here in terms of these inequalities and vectors. Okay, now amplituhedron is a larger class of some more complicated geometries. So since it was found, we know a little bit more for also different quantum field theories. I said that this was just for these theories of gluons, but we know a little bit more, but we still don't know. It's still a big open question how it actually works for the other quantum field theories. Yeah. For example, for the standard model, how it actually interplays with gravity. Yeah, we said that there is this big problem with gravity. Can we do any calculation? Is there any geometry for gravity amplitudes as well? Yeah, we don't know. Okay, so now going back to the question, what is the scattering amplitude? So at least for certain cases, yeah, there was also some little bit disclaimer. This geometric picture for strong interactions works with some specific case. You have to add supersymmetry. Yeah, so there were some caveats. So there is a lot more to understand how it works in the case of actually QCD, quantum chromodynamics, in the real world, because as I said, there is this huge subtlety that there are not only these gluons and quarks. They only exist at high energies. If you go to low energies, there are protons and neutrons. Yeah, so that's not clear how it fits into this geometric picture. Yeah, here you only have gluons and quarks. Anyway, but even if it was one specialized case, in this case we have a new answer to the old question, what is the scattering amplitudes? And it's a volume of certain geometric object. Yeah, and know that this is very different. It's a very different description as before. Yeah, because before we were talking about particles, interactions. Yeah, you smash them together, they produce a new particle, and so on. So there is some complicated physics dynamics, but this new description is completely static. Yeah, it tells you that you should build some geometry and calculate its volume. It's completely static. It knows nothing about particles and interactions, yet it calculates the same object. So yeah, so it's extremely mysterious. Like, what is the physics origin? Or maybe the right question is that it's a mathematical way it's a mathematical origin of quantum field theory here. Okay, but yeah, there are many more. Yeah, it's really just the beginning of a very long road. Because also the quantum field theory as we learned in recent years, is not just about these scattering amplitudes. There are other interesting objects that can be calculated, and the question is how they fit into this story as well. But let me end with kind of a fantasy where this thing can lead, or might also not lead, who knows. And it also explains why it's interesting to have a thing beyond just kind of computational efficiency, which is a good argument by itself, but there is an additional benefit or additional value of having two different descriptions of the same thing. So, and it goes back to the classical mechanics. In the classical mechanics, there is classical determinism, which means that if you tell me the initial conditions, you tell me what are the equations of motions, I can just predict everything. I can predict how objects move. Yeah, it's completely deterministic. And this is formulated using Newton's equations. However, there is an equivalent description of classical physics using action principle. Okay, and the path integral and Lagrange equations. And here, despite it describes the same classical physics, which is deterministic, the mathematical description doesn't have determinism in it. Yeah, so you are probably familiar with this picture. So you have point A and B, and in this action principle, there are different paths between point A and B possible. However, the equations of motions pick exactly the straight path. So that solves the equations of motion, and then it agrees with the solution of Newton's equations. However, the mathematical formalism of action principle allows for many other trajectories, yeah, which just are not selected, but yeah, but they are there. Yeah, it is allowed. The determinism is not manifest in this description. Now, this is very important because eventually the determinism is gone and the quantum world is probabilistic. And these other paths actually do exist. Yeah, they are there and they can happen. It's just that they happen with at much lower rate. Yeah, they are much less probable than the straight classical path, but the other paths do happen. And this corresponds also to the fact that if you take the quantum field theory or quantum mechanics and you do the h bar goes to 0 limit, you suppress the quantum effects. What you land on is the action principle, not the Newton's equation. Yeah, because the Newton's equations have this determinism in it, and it's just incompatible with the quantum description of the world, while the action principle allows this extension. Yeah. Okay, so therefore here it's very important that we have this second description, and that's actually how people discovered quantum mechanics in the first place, that they already had this formalism in front of them, but of course they had to do this huge leap from the classical to quantum to allow for this probabilistic behavior. Now, so here the question is, how is it with quantum gravity? We know that the quantum field theory as we know it, using these Lagrangians and fields and amplitudes and so on, is incompatible with quantum gravity. The reason why it's incompatible is that you cannot really talk about local interactions. You cannot really, in quantum gravity, you cannot say that particles interact in one point. Yeah, because there is some problem with identifying that point. Yeah, I wouldn't go into details, but now the standard formulation of quantum field theory has this picture of interactions. It's built in. So it cannot do anything with that. So yeah, that's called locality. The fact that they interact in one point, it's also referred to as locality. And it's manifest in QFT and it's absent in quantum gravity. So if we have a theory of quantum gravity and now we remove gravitational effects, so we set some gravitational constant to 0, we cannot possibly land on the quantum field theory formulation as we know it, because of this two principles, because of this principle being treated so differently. So the idea is that if there is an equivalent formulation for the quantum field theory, which does not have locality manifest, doesn't rely on the fact that you have particles interact in a point, then this should be the formulation where some non-gravitational limit of quantum gravity turns in, like the correspondence between the quantum field theory and the action principle. Now, the thing is that in this new geometric formulation using amplitude-hedron, as I said, there are many things to be done here. It's far from done. But in that formulation, the locality is not manifest because we are not even talking about particles there or interactions. We are talking about geometry. Yeah. So one can imagine that you just have to deform the geometry to make it gravitational, but the geometric picture itself would stay. But but there is some gigantic leap to do. But yeah, it's at least a promising start. Okay, now let me just end with that. We have actually a theory of quantum gravity. I already said that before, and it's called string theory. And exactly it avoids this problem of local interactions because there are also no particles. So there are no particles meeting at a point. Instead of particles, we talk about strings. So the corresponding Feynman diagrams for strings look like that, and they don't have any points. Yeah. But the current formulation of string theory looks much like Feynman diagram. So this really looks like Feynman diagram. So there is a question, is there some new geometric picture for strings? Maybe that is the ultimate question that we would like to understand. And that would be closely connected to this picture for quantum gravity. Okay, thank you for your attention. Okay, are there any questions?
Thanks, Dr. Trnka. Yeah, I just had a question about the when you were talking about like the GG to GG problem, for example. Do you like do any computational basis for solving this, or is a lot of your work still like making diagrams like you were talking about with string theory, and like still doing a lot of the drawings and work by hand?
No, it's so sorry. You mean like this problem, or I was saying here that the geometric picture just reformulates the physics problem of drawing these diagrams and evaluating them into a mathematical problem, and it's a set of inequalities basically that you have to solve. So the thing I kind of showed here is what these inequalities are, yeah, what is their meaning. But in the end, you have to solve some set of quadratic inequalities. If you solve them, then you can basically turn that solution into some function, and that function will be a scattering amplitude, and this will be equal to the sum of Feynman diagrams. Well, beyond just kind of the theoretical difference that this is some geometry, and then we were talking about particles and interactions, the main practical difference is that here the kind of the mathematical description is for any number of loops. Yeah, so it kind of covers infinite number of Feynman diagrams at once. Yeah, because in this expansion that I showed in the beginning, kind of here, this perturbative expansion, if you go to higher and higher order, this is what was called the loop expansion, right? You have to draw more and more Feynman diagrams that you would have to calculate. And if you go to infinite number of loops, you have just to calculate infinite number of diagrams. Yeah. So this picture of Feynman diagrams is just extremely bad in making some general statement. Yeah, you have to kind of do it order by order, and you always have to start from scratch, and you have to draw more and more diagrams and evaluate them. And this geometry just kind of gives you the definition all at once. Now the question is, yeah, you have to solve this mathematical problem, but the mathematical problem is at least posed for arbitrary case. Yeah, while in Feynman diagrams, you don't even have the problems posed. Yeah, the problem is like draw infinite number of diagrams. Yeah, that's not, yeah, it's not something you can start with. Yeah.
I had a question with regards to, I think on one of the slides you mentioned there's a problem with something called supersymmetric localization. So I'm vaguely aware of what supersymmetry is and how, unfortunately, I think we have yet to prove, experimentally at least, that this is a viable phenomena. So what exactly is that problem?
This kind of thing, I didn't get back to it, but these are different methods how to do calculation in quantum field theory. Now, the supersymmetry is a principle which, as I said here, kind of tells you that in addition to the standard model particles, you have also these super partners. We haven't observed them. Maybe they are just too heavy. We will have to go to higher energies. The supersymmetry as a principle is an interesting phenomenon in quantum field theory, regardless if it is there in the real world or not. Yeah, and it solves many of the problems with the standard model. Yeah, but maybe it is not the way how the nature works. Who knows? Yeah, it's kind of the leading candidate, but who knows? But regardless of that, you can just study it theoretically. You can have quantum field theory, and you say that it has a supersymmetry, and then it has some special properties. Yeah. And then you can use the supersymmetry to also solve certain questions, like give answers to certain questions in quantum field theory. Yeah, calculate certain things much more easily. And yeah, so this was one way how to do it. There are also other ways how in some special quantum field theories to do calculation. But the thing is that all these kind of methods are like one by one. Yeah, they are not covered by some bigger umbrella of a general framework. Yeah, so they are kind of not compatible with this picture of Feynman diagrams and Lagrangians, which is general, and this is the way how we think about quantum field theory. But in individual cases, you can do more using some special properties. But we don't have a general story, yeah, about it. So that's what I was trying to say here. The same thing with these dualities. Yeah. Case by case, you can see that there is a duality between some weakly coupled and strongly coupled system. But yeah, how do you know that it's there unless you actually find it? Yeah, and can you see it from some Lagrangian or something? Yeah, these are the things that we don't know. Yeah.
Okay, gotcha. One other thing, this might just be because I'm not entirely familiar with the Feynman diagrams, but when you had the equation up showing all the different diagrams, the coupling constant increases by a square. So you had like q squared and q to the fourth. Does that correspond to like the number of vertices per each diagram?
Yeah. Okay. Here it's just the number of vertices because they kind of they come in pairs. Yeah. You cannot have 3 vertices. So yeah, so that's exactly, it just counts the number of vertices, and the diagram with more vertices is just more complicated and has more of these internal loops necessarily. Yeah.
Gotcha.
So,
all right.
Yeah, exactly.
My last question here is I know there's this thing called quantum loop gravity. That's like another, or maybe it's just loop gravity. That's another. So is that wholly incompatible, or is there like some? Is it just like a separate school of thought, or?
Yeah, it's a very different way how to treat things because, yeah, I'm not an expert on that. It's kind of or people who do it consider it to be like competing with the idea of string theory, but so far it hasn't produced any results. Any kind of results that can be compared with anything, but it has a very different idea. So it doesn't kind of build on this picture of quantum field theory, but it changes kind of the notion of the space-time itself. Yeah. So we have a problem with incorporating gravity in quantum field theory because kind of there are many features of the gravity which makes it hard to think about it in this context. One of them is that when you do the scattering of particles, if things scatter in one point, it means from just uncertainty principle in quantum mechanics, it means that in order to kind of to zoom into one point, you need more and more energy, yeah, to actually see that it interacts in one point. And in gravity, if you accumulate energy in a very small volume, the energy itself is equivalent to mass, and it forms a black hole. And when it forms a black hole, you cannot access that information anymore. So there are many problems like that with the gravity, and therefore it's incompatible with quantum field theory, because how do you talk about scattering if you just create some black holes in the middle and you completely lose the information? Now the loop quantum gravity tries to handle it differently, so it has a different notion of what the space-time is itself. Yeah, what is the from what the space-time is made. So it doesn't build on this picture of the quantum description. Yeah, but I'm not an expert in it. But unlike the string theory, which gave different predictions, of course, we haven't seen strings in the world, but there are certain things that you can calculate, and then you can kind of go into the non-string limit. Yeah, you can kind of go to the low energy limit where the string states don't exist. So you just the regular states that you see, like gravitons and gluons are, and you can make certain predictions and you can compare it from other things. But yeah, but the loop quantum gravity, as far as I'm aware, haven't really produced any predictions like that. Yeah, but it's also based on a very different idea.
Thank you. I'll see if anyone else has any more questions. It's like one thing off the top of my head, but I just want to make sure everyone else has a chance to ask away.
Sure.
In that case, I'll just go for it. But what happens if you know, I see there's, you know, supersymmetry does give a lot of very nice properties, and I know it answers some. I guess it hammers out some of the uglier math. But what happens if we don't find like any proof that not string, sorry, supersymmetry. Excuse me, supersymmetry is what I'm. What if we find out like supersymmetry was a farce? Like there is no nice correspondence between bosons and fermions, and it's just.
No, well, yeah, it's just okay. The supersymmetry doesn't have to be in the real world. Yeah, there is a separate question if you want to study supersymmetric for kind of theoretical or mathematical purposes. That's completely fine, and people do it and will do it regardless if it is found or not. But we know that there is some beyond standard model physics. There are just certain. The standard model itself is not a consistent theory to all energies. Yeah. It's perfectly consistent if you are at low energies or up to certain cutoff, up to certain threshold. But if you go to very high energies, there are just problems. Yeah. In other words, if you use quantum field theory, it generates certain divergences. Yeah. In essence, the amplitude is infinite. Yeah. So there is some inconsistency, and you have to cancel these infinities. And supersymmetry is one way how to cancel these infinities. It tells you that in practice, when you calculate these loop diagrams here, like the diagrams that were here, the result for this diagram is actually infinity. Okay, and there are two ways how you treat it. The infinity is there because these particles which are on these internal lines, these are called virtual particles. They are not real. Yeah, they are just inside that Feynman diagram. They can have infinite energies. The only thing that you have to satisfy is the kind of energy conservation in each vertex. But if there is a particle which kind of flows around and has infinite energy, it's perfectly allowed by all conservation laws. And these particles produce infinite contributions to amplitude. So there are two ways how you can treat it. The one way, and this is in the kind of in the framework of effective field theory, you say that these internal particles are not allowed to have any energy, but there is some cutoff, there is some maximal energy they can have. And then it's not infinite, then it's regulated and everything is fine. but you are saying that your theory is only valid up to this cutoff. Yeah, it's not valid for higher energy than that. And but the more ambitious is to find some mechanism how to cancel these divergences directly. Yeah, not just to kind of use this cutoff and just to cut them in this little bit artificial way. And supersymmetry is one way how to cancel it, because it tells you that in these loop diagrams, you can have fermion or boson, which are related by supersymmetry, and they have the same divergence with different signs, and it just cancels. Yeah, so it's a most elegant way how to deal with this problem. It's not the only way, but it's the most elegant and direct way. But of course, the nature doesn't have to work like that. Yeah, nobody, the nature probably doesn't care about if we are playing with Feynman diagrams or doing that. But we are not aware of any other mechanism which would do it. Yeah, but something must happen. It cannot be that the standard model is end of the story and that's it. Yeah. There must be some new physics. So the question, what type of new physics is there? And whatever it is, it must explain this problem. Yeah.
All right. Thank you very much for answering that. I think I'll, if there are any further questions, because I recognize we're going a little over time. So, hey, I don't think so. But before we conclude everything, I just want to say that the recording will be on the quantum computing at Davis website. It should be under the workshops tab for this quarter, so it will get uploaded soon. But once again, Professor, thank you so much for your time. It was a wonderful presentation, and I think both the Physics Club and us are very appreciative of the work you've put in. So thank you so much.
Okay, thank you very much for inviting me. Have a good day, everybody.
Thank you. Have a good day.